So in the last video we derived this relation. Now this torque causes the angular momentum to change according to the relation, because torque is equal to rate of change of angular momentum. Now suppose I will plot a figure here. This is tau, which is rate of change of angular momentum. Angular velocity is defined as we call it omega L due to orbital motion of electron, which is equal to rate of change of angular displacement. Or we can say that d phi is equal to omega L dt. This is equation number 6. This will be the equation number 7, and this is equation number 8. Now I will plot that figure again, the precision figure. Suppose we have an electron which is moving in this elliptical orbit, and here we have the external magnetic field B, and the orbital angular momentum vector direction is this one. It persists around the external magnetic field this way. So this vector L move from this point to this point. I call it point A. I call this is point B. So we have draw perpendicular here. This is now angle 90. I call this angle as theta. So this is L, this is theta. So this part will be L sin theta. So the projection from here to this point is this one. I call this angle as d phi. Now this is the arc length AB. If let's suppose this is point A. If I consider the triangle OAB and triangle OAB, so this is the triangle OAB. This is same like, let's suppose we have a circular loop and we have this radius R, and this particle move from here to here. Then this arc length, arc S, is related to this R in theta by S is equal to R theta. Now here the angle here is d phi and the arc length is AB, which is basically, this is L move from here to here, so this is basically dl, change in L. So the arc length, arc, which is dl, is equal to radius is this one, and this component is L sin theta. L sin theta times the angle d phi by using this formula. Now this is the arc length, because the angular momentum vector L move from here point A to point B. So this is the change in angular momentum delta dl. Now this component we already calculated, it's L sin theta, because this is angle theta. So this is the projection is perpendicular. So this time this is perpendicular, and perpendicular is equal to L sin theta, and this is the hypotenuse. This is the base. Now this dl, this arc length dl, is equal to this radius, which is L sin theta, and we have this angle d phi. From this we calculate the d phi, which is equal to dl over L sin theta. This is equation number 9, let's say. Now comparing equation 8 and 9, we have equation 8 is this one, and equation 9 is this one. Both the left hand side of both these equations are same. So if we compare both these equations, we get omega L d T is equal to dl over L sine theta. Omega L is equal to the angular velocity due to orbital motion of electron is equal to dl over dt into 1 over L sine theta. Now this dl over dt is equal to the torque from equation 7. So we have omega L, which is equal to torque over L sine theta. And torque value is itself mu L b sine theta. So if we put equation 6 here, we have omega L is equal to mu L b sine theta over L sine theta. Now sine theta cancel with sine theta. So we have this angular velocity omega L, which is equal to mu L b over L. Or we can say that omega L is equal to mu L over L into b. Now we have equation number 5 given here, which is magnetic moment, the ratio of magnetic moment and orbital angular momentum is equal to charge over 2m, E over 2m. So if I replace omega L is equal to this term by this E over 2m into b. So we have omega L, which is equal to EB over 2m. Now the angular velocity and angular frequency are related to each other. The angular frequency velocity is related with angular frequency by the relation, and the relation is omega L is equal to 2 pi nu L, or we can say that omega is equal to 2 pi nu. So if I put, let's say this is equation number 10 and this is 11, comparing equation 10 and 11, we have 2 pi nu is equal to EB over 2m, or we can say that angular frequency is equal to EB over 4 pi, and this is the proof of Larmos theorem, because we have the Larmos theorem which we define here. This is the Larmos theorem, which says that the frequency of precision nu L is equal to EB over 4 pi m. So here E is the charge, B is the external magnetic field, and m is the mass of electron. So we prove the same formula here. So the frequency of precision is proportional to the magnetic field. Stronger the magnetic field, greater will be the frequency of precision, because the rest of the quantities are all constant. Charge of electron is constant, 4 pi is constant, mass of electron is also constant. So it means that this equation implies that frequency of precision is proportional to the external magnetic field, and this is Larmos theorem. So this is the end of Larmos theorem, and in the next video we will move to the Pauli exclusive principle. Thank you.